Okay, imagine this. A future where your most sensitive data, think financial stuff, national security secrets, everything is protected by the actual laws of physics, making it, well, fundamentally unhackable. Sounds a bit like science fiction, doesn't it? But, the cutting edge of communication is actually turning that into reality, and pretty quickly. Welcome to the deep dive. Today, we're diving headfirst into quantum communication. And this isn't just theory anymore. It's a field that's developing really fast using those, frankly, mind bending quantum mechanics principles for ultra secure data transmission, tamper proof, even. So, our mission today is simple. We want to pull out the most important nuggets from all the sources you gave us, articles, research papers, notes, the whole lot, and basically get you up to speed on quantum communication. Quickly, we'll highlight the really compelling bits, the surprising insights, give you a solid understanding. So, okay, let's start unpacking this. It's a fundamental shift, right? We all know classical computing, bits, zeros and ones. They power everything, our phones, the internet, all of it. But quantum communication. It takes that idea and completely redefines it with qubits, quantum bits. Now, the key thing about these qubits, the really crucial aspect, is they can be in what's called superposition. So imagine a qubit being like both a 0 and a 1 at the very same time, holding all possibilities until you actually look at it. This ability to be in multiple states at once is absolutely central to how quantum communication works. And then there's entanglement. This is where it gets really interesting, maybe a bit weird. You have particles becoming linked, intrinsically linked, so the state of one instantly influences the other, no matter how far apart they are. Miles, light years, doesn't matter. So hang on. If I'm getting this right, it's like they share a secret. And when one reveals its part, the other instantly knows, across any distance. How is that not sending information faster than light? That sounds like it breaks physics.
Yeah, that's a really common question and a great one. It gets right to the heart of entanglement subtlety. It's super important to understand. It's not about sending classical information faster than light. No actual data, like a message, gets transmitted just through entanglement itself.
Okay.
Instead, it's about this immediate correlation, this linked relationship. You measure one particle, and instantly, you know the state of its entangled partner, wherever it is. It's this instantaneous correlation across, potentially vast distances that makes it so powerful for secure communication. But it doesn't violate relativity. No information transfer faster than light.
Got it. So correlation, not communication in the classical sense. And building on that kind of inherent quantum weirdness, there's the no cloning theorem, which basically says you can't perfectly copy an unknown quantum state. It's physically impossible. And this impossibility gives you this like built-in security layer. It's fundamental, right, in the physics, not like classical encryption, which just relies on math problems being hard.
Right, exactly. Which then brings up a critical point.
Mm-hmm.
If you can't copy it, how do you even know if someone's trying to eavesdrop?
Right.
And that's where quantum measurement is key. The very act of observing, of measuring a qubit, actually changes its state. It alters it.
Ah.
So this means if some eavesdropper, let's call her Eve, tries to intercept the quantum signal to read it, she has to measure it. And by doing so, she inevitably disturbs the qubit. She leaves a trace.
A detectable trace.
Precisely. That disturbance is immediately detectable by the legitimate parties, Alice and Bob. It's like a built-in alarm system for your data, It inherently reveals any attempt to listen in.
So just trying to spy messes things up and gives the game away. That's incredibly elegant and totally different from classical methods where someone might copy data without you knowing for ages.
It really flips the script on interception.
Absolutely. But okay, these concepts, superposition, entanglement, no cloning, they're fascinating. But how do we actually use them? Let's talk about the technologies making this happen. Right now, the most developed, the most mature protocol seems to be quantum key distribution, QKD. And its whole purpose, pretty much, is just to securely exchange encryption keys using those quantum principles we just talked about to make sure the key shared between two people is absolutely secure. Tamper-proof. You hear about protocols like BB84 uses polarized photons, or E91, which uses entangled pairs. These are common ways QKD is done.
And the significance of QKD is just immense.
Yeah.
Because it offers a way to generate and distribute encryption keys that are theoretically unbreakable, even by future quantum computers, which are a huge threat to current encryption.
Right, the whole post-quantum concern.
Exactly. So this isn't just, slightly stronger encryption.
Yeah.
It's a whole new paradigm for secure data exchange, truly ultra-secure.
Okay, but there are practical challenges, like distance, right? These quantum signals must be fragile. So just like any signal, they degrade. Especially in fiber optic cables, they lose strength, lose their quantumness. which is why we need things like quantum repeaters.
Hmm.
These devices are basically designed to extend the quantum signal over longer distances, to counteract that signal loss and also this problem called decoherence.
Right. Decoherence is a big one. It's when the quantum state just kind of fuzzes out because of interaction with the environment, heat, vibrations, anything.
Destroys the quantum magic.
Pretty much.
And then to build a real network, not just point-to-point links, you need quantum memory. Tech that can actually store this delicate quantum information for later. Hold on to those states long enough to, process them or pass them along. Crucial for scaling up.
And connecting all these pieces, especially for overcoming distance limitations on the ground, is satellite-based quantum communication. This is really exciting stuff.
Using satellite.
Exactly. You bypass the limitations of terrestrial fiber, use satellites to beam entangled photons between ground stations potentially continents apart. And this isn't just theory. China's Messiah satellite, launched way back in 2016, actually did this.
Wow, 2016.
Yeah. Successfully transmitted entangled photons over pretty significant distances. It proved space-based quantum communication works. It's a real capability pointing towards, future global quantum networks.
That's incredible. Misha showed it's happening now. So, okay, we have the principles, we have these emerging technologies, QKD, repeaters, memory, satellites. What does this all actually mean for us, for securing data, for the future? What are the applications? Well, the most obvious one is ultra-secure data transmission, like we touched on. Military, government, big financial institutions. They could exchange data with encryption that's, virtually unbreakable based on physics. It's a total game changer compared to current methods.
Absolutely. And thinking bigger than just secure links, there's this grand vision of a quantum internet. Imagine a global network using quantum signals, not classical ones, enabling things like instantaneous, entanglement-based communication over vast distances. It could unlock entirely new capabilities, distributed quantum computing, maybe even things we haven't thought of yet. Plus, incredibly secure global communication.
Wow. A whole new internet. And what about the cloud? So much of our data lives there now. Does quantum help with secure cloud computing?
It definitely has huge implications there. Right now, we trust providers, but there's always a risk. Imagine using quantum keys, generated via QKD, to protect data going into and out of the cloud. It could make cloud environments vastly more resistant to sophisticated cyber threats, even future ones.
Protecting data even when it's not directly in your hands.
Exactly. And then, of course, there's defense and intelligence. For them, quantum communication is absolutely critical. It's key for developing post-quantum cryptography. Basically, preparing for the day when powerful quantum computers might break current encryption standards.
Future-proofing security.
Right. Ensuring national security communications remain robust against even the most advanced future threats. It's a massive strategic priority.
Which explains why this isn't just research anymore. It's become this intense global race, hasn't it? Nations are pouring money into this.
Yeah, absolutely. Look at China. They're widely seen as a leader, especially in QKD and satellite quantum stuff. They built that Beijing-Shanghai quantum communication line over 2,000 kilometers. That's not a lab experiment. That's real infrastructure, like an internal, ultra-secure government network.
Huge statement of intent.
Totally. Then you've got the European Union with its EuroQCI initiative, planning a whole continent-wide quantum network by the 2030s. The U.S. has the Department of Energy's Quantum Internet Blueprint, lots of R&D at DARPA, NASA, the national labs. Canada's got the QEYSat project, focusing specifically on satellites for quantum communication. And India just launched a huge national quantum mission, like over $1 billion, aiming for secure QKD networks and their own quantum satellites by 2031. It's really striking, isn't it? The sheer scale of the investment, billions being committed globally. It just underlines how strategically vital everyone sees this. It's not just about science. It's about future economic leadership and, crucially, national security. It's a race for digital sovereignty, really.
Definitely feels like a race. But okay, despite all this progress and investment, let's be realistic. There must be big challenges still. It can't be easy.
Oh, absolutely. Huge challenges remain. This tech is still, pretty difficult. First off, signal loss, like we mentioned. Quantum signals are super fragile. They degrade much faster than classical signals in optical fibers, limiting distance.
Right. Maintaining that quantum state over distance is tough.
Then there's decoherence, that environmental interference problem. Any little vibration, stray light, heat, it can just destroy the quantum information.
Often requiring really complex, expensive isolation, like cryogenic cooling sometimes.
Yeah, which leads to cost and infrastructure.
Yeah.
Building this stuff requires specialized, very expensive hardware, and maintaining it isn't cheap either. It's not off-the-shelf tech yet.
Not at all. Plus, there's a lack of standardization. No global agreement yet on the best protocols, the hardware specs, how things should connect. That slows down wider adoption.
Everyone's kind of doing their own thing in some
Yeah,
ways.
exactly. And finally, scalability. Going from these sort of point-to-point QKD links to a full-blown quantum internet connecting millions, that's a massive engineering and logistical challenge. Really complex.
Yeah, those are definitely significant hurdles. It does temper the excitement a bit. Makes you wonder, how will these practical issues affect the timeline? And, who gets access? Will it just be for governments and big corporations, or will it eventually reach, say, everyday consumers? That's a big question.
It is. But looking at the projections, the roadmap people are putting out,
Yeah.
it seems there's confidence these challenges are being tackled pretty aggressively. Some sources predict quite rapid milestones, actually, like by 2025 to 2027, so pretty soon we could see more widespread QKD being deployed in major cities for sensitive sectors like finance and government.
Okay, so initial focus rollouts.
Yeah. Then, maybe 2028 to 2030, you start seeing hybrid networks becoming common, blending classical infrastructure with quantum links for key distribution.
Makes sense. Leverage existing networks where possible.
Right. Then the next big step, maybe 2030 to 2035, could be the launch of actual regional quantum internets. The first true quantum backbones in places like China, the EU, North America.
Wow, regional quantum internets within about a decade.
That's the projection. And looking further out, beyond 2035, the vision gets really ambitious. A global quantum internet. Quantum cloud computing becoming standard. Even things like teleportation networks for secure data transfer.
It's startling how quickly this field is expected to move. From labs to potentially global infrastructure in maybe 2 decades. It really shows the intensity of the R&D effort worldwide. What seems like sci-fi today could be foundational tech sooner than we think.
And that speed, that potential, explains the huge economic and strategic stakes we talked about. Economically, the numbers are already getting big. The global quantum communication market, projected to blow past $10 billion by 2030.
10 billion.
Wow.
Yeah. And you've got major industries piling in: telecom, cybersecurity, aerospace, cloud providers. They all see a massive new market forming. Huge opportunities.
And strategically, as we said, the impact is arguably even bigger. Nations that get ahead, that build and control advanced quantum networks, they'll have a massive edge in cybersecurity, definitely, but also surveillance, defense capabilities.
A strategic advantage.
A decisive one, potentially.
Yeah.
This is seen as critical for next-gen national infrastructure resilience. It's really a competition for cyber sovereignty, for defense dominance in the coming decades. It's more than just business.
What an incredible journey we've taken today. This deep dive really shows quantum communication isn't just an incremental improvement. It feels like a truly transformative leap in how we secure information, how we share it, maybe even how we understand it.
I agree completely. It's definitely not just some far-off futuristic curiosity anymore. This is happening now. It's a rapidly developing field. And the implications, as we've discussed, are profound for everyone.
Absolutely. Which leaves us with a final thought, something for you, our listeners, to consider. Given these projected timelines, this breakneck pace, and this intense global race for quantum dominance, what does this all actually mean for the future? For your privacy, for national security, for the very fabric of the internet as we know it today?